Hello. Welcome to this second keynote session of PEPM. This keynote will be given by Xinyu about reasoning about progress of concurrent programs. So Xinyu did his PhD at Yale with Zhang Xiao, right? And has a, so you went back to China after that, where you now have a successful group doing research in programming languages, many distinguished paper awards. I think the recent one on PLDI from, and lots of research fundings and impressive CV. Without further ado, I'll leave the floor to you. Thanks.
Thanks. Thanks for the invitation. So the talk is about, actually it's about concurrency verification. And I'm sorry, probably there's not much about program manipulation, but hopefully concurrency is an interesting enough topic, and this talk will bring you more insights about concurrency. So let me first introduce the basic model we are talking about. So what is a concurrent object? It's just an encapsulation of some data with a set of methods. So these methods are the only approach that you could use to access the data. And then a concurrent object is just an object that could be used by concurrents with multiple threads, which means in these different threads, they could call the methods. So at the same time, you could have multiple threads executing the same set of methods from the same object. So then, which means that this data is shared by these concurrent tasks. So there are many real-world examples of concurrent objects. For instance, in the concurrency package of Java, we have many implementation of concurrent objects. And here we just show one simple example. So it's a concurrent counter here. So this is this integer representation of the counter is the object data, and this inc is a method which increments the counter by 1. And so this is a very simple algorithm, but it accesses the shared variable counter without using logs. So it's a non-blocking implementation of counter. So what we do here is inside this loop, we first take a snapshot of this shared variable, and we store it into the local variable. And then we do this atomic compare and swap operation. So what it does is it compares the current value of this counter with this snapshot. And if they are the same, then atomically it puts this third value, 10 plus 1, to the counter so that we finish this increments, it returns true, and then this loop terminates. Then we are done. Or if the counter could be different from temp because we are different concurrent setting, so the current thread could be interrupted after line 4, so that at line 5 the counter could have a new value, so the snapshot could be obsolete. Then in this case, the cast does nothing; it returns false. So we have to do another round of loop. Okay. So this is a very simple algorithm. It's like the hello world example for non-blocking algorithm. But then the question is still, is it correct? And if we discuss about correctness, how do we first formalize this? And we probably know that linearizability has been one of the classic formulation of correctness of concurrent objects. And it specifies the correctness in terms of functionality. Essentially, it says the methods of the concurrent objects should be viewed as some atomic operation that finish the functionality. And so from client point of view, it doesn't have to worry about the fine-grained interleaving of these methods. But the problem is it doesn't guarantee termination. So it's like when you do whole logic reasoning, it's like the partial correctness is instead of total correctness. It doesn't guarantee, it doesn't say anything about termination. And if we worry about termination, so here we know that from the object point of view, the method could be executed by different threads. So the progress of a concurrent object essentially specifies the termination property of the method. So in a sequential setting, termination is very simple. but it's, at least it's easy to understand what we mean by termination. But in a concurrent setting, actually it's a lot more complicated because the behavior of the thread could be affected by the behavior of the other threads. So that's why if we look at the literature, there have been many different variations of progress properties proposed. So we have these many different variations. And you probably have heard that the first three actually refers to describe a non-blocking algorithm, and the last two specifies so-called blocking algorithm. So in this talk, actually, we mainly explain what do they mean and what are the key differences. And if we want to verify the progress properties, what do we do? So in this talk, we first give an informal explanation of the progress properties of concurrent objects. In particular, we want to introduce the two key factors that affect progress, which we call blocking and delay. Then, based on this understanding, we propose a new Hoare-style program logic to verify progress. Actually, it gives us a uniform framework to reason about all these different progress properties. And also, I want to clarify here that this verification work is not about automated verification. It's more like designing a new set of horological rules. Or you could view it as some kind of axiomatic semantics of concurrent objects. So hopefully it may serve as the basis for future work on automation, but the work itself is not worried about decidability or complexity. So first, this is the basic language we use to describe the concurrent algorithm. So this is just a very simple while language that we use to design Hoare logic. As you could see, there's even no concurrency. It's just a sequential program. This is because when we write the method code, object method code here, it's implemented as a sequential program. Although the client may be concurrent, so here we have multiple threads in the client, but in the object code, it's just implemented as a sequential code. Also, we want to emphasize here, we only have we don't have any function calls. So these while loops are the only source of possible non-termination. So this simplifies our discussion. We don't have to worry about recursive functions. Okay. And so then, how do we reason about termination? As I said, we only need to worry about this while loop. And so here, if we consider what we do in a sequential setting, actually, essentially, we make sure there's no infinite loops. We ask the while loop to, for it to terminate, it needs to wait for a certain condition in Q, so that this Q eventually leads to the negation of B. And if B is false, then this loop terminates. Okay. Then in a concurrent setting, so it's more tricky because usually the formulation of Q may involve shared variables, then which means that the behavior of this environment, by environment I mean the set of all threads in the system. So the behavior of the environment may affect the validity of Q. So then when we reason about when we think about the Q, we have to think about the environment behaviors. So I can show you this counter example. Then this case, actually, as I explained, it may fail because it may be interrupted after line 4. And so if there's another thread, let's see, in this infinite loop, it calls inc, then this case may always fail. It's possible to never for this inc to do this loop forever. And so here, this Q that we use to reason about this termination is that this temp snapshot value equals to the counter. So if this is Q holds, then we know that down will be true. So then this loop will terminate. But then the behavior of this environment may make Q to be false. So then this is another example. It's a simple test and set implementation with spin lock. So in this lock acquire method, we in this loop, we test whether the lock bit is 0 or not. 0 means it's available. If it's available, atomically we set 1 to the lock bit, so it acquires a lock. Then this loop terminates. Otherwise, it has to do this busy waiting, has to wait until the lock is available. And again, this case may fail, which this is caused by the case in other threads, if other threads has already acquired this lock. So in this case, for the queue, it says L equals 0. So if L equals 0, then case will succeed, then will be true. So this loop will terminate. And so then the key here is to find this queue to make sure it will guarantee termination. But then after we find this queue, the first question we need to ask is that since it could be made false by the environment, then the first question we ask is, can the current thread itself reestablish queue when queue is false? Okay, so this is important because if the answer is yes, then like this example, so if queue is false, we fail, we do another one loop. So we redo the snapshot step. And so, and then essentially it reestablishes queue, and hopefully next time the case succeeds. So, which means the thread itself could reestablish queue in this example. Or in this case, we call this non-blocking algorithm. There are other examples. For instance, for this lock acquire, then the thread itself cannot reestablish queue because here, when the lock is not available, so queue is false, then the thread has to wait for other thread to release the lock. So in this case, it cannot make queue to be true itself. Okay, and then so essentially the current threads rely on the other threads to make progress. In this case, we call this kind of algorithm blocking algorithm. So we could see that essentially any algorithm that involves locks cannot be non-blocking. It has to be a blocking algorithm. Also, it explains why we say that blocking algorithm actually relies on fair scheduling to eventually make progress. Because if you see here, if the thread waits for the availability of the lock, which means the lock has been acquired by others, and if the current owner of the lock is not scheduled, so even the code itself is good, but if it's not scheduled, then that thread has no way to release the lock. Then the thread waiting for the lock then have to be will never get the lock. So which means there's no chance for it to progress. So which means that for blocking-based algorithm, we have to rely on fair scheduling to really get progress. And so then, so this. As we see, whether this current thread could reestablish queue or not, split the algorithm into two categories: non-blocking and blocking. We first look at this non-blocking category, and so the next question is: if the queue becomes true, then could the environment again turn it to be false? Okay. Actually, in this example, still this is a counter example. So even after it's step 4, it reestablishes this queue, it could be interrupted again by this environment. So the environment may take a queue from true to be false again. So in this case, we call it a delay. This delay operation actually causes the current thread to do more loops. It's not really very harmful, but it's just so in the sense that if we suspend the environment, then the current thread would eventually progress. But if the environment is active, it may cause the current thread to do more loops. So, and in this case, the delay may happen infinite many times. Okay. Then essentially we have to ask whether Q equals to true will be eventually stable. If it will be eventually stable, which means it can no longer be affected by the environment, which means there's only a finite number of delay. Okay, and if this condition is true, then this kind of algorithm is called a wait-free algorithm. It relies on, it says there's no blocking allowed, and it only allows finite. There's only finite number of delay. So if we look at the official definition of weight freedom, it says so in a concurrent setting, every object method call must always return. So this is a very strong property here. And if this is not true, which means there could be infinite delay here, then we have to ask another question, which is the environment is making progress? So still we look at this example. So this case may always fail, as I explained, but this is bad since it may never terminate. But on the other hand, it might be acceptable because this failure is caused by the successful case from this environment. Okay, because this, if we look at the whole system, then there's always some method call of ink that terminates. So in this sense, it's still acceptable. So which means if the environment is making progress, then it's another category of algorithm which we call log freedom. And it says it's non-blocking. It allows infinite delay, but the environment has to progress. Okay, and so if we compare with weight freedom, log freedom says there always exists at least one method call that returns here. And if this is false, so the environment is not making progress, then this is the so-called obstruction-free algorithm. It's non-blocking. There might be infinite delay, but still it's not too bad because if we look at this example here, if we have two threads, M1 and M2, executed in parallel, M1 just increments the value of I until it reaches 10, and M2 decrements it until it reaches 0. Suppose the initial value of I is between 0 and 10, let's say it's 5. Then neither of the methods may terminate. It could be for both of them to do infinite loop. But if we suspend any of them at any time, then the other thread will eventually terminate. So this is the so-called obstruction freedom. It says at any time we suspend all threads except one, then the method call in the remaining thread must always return. Okay, so and we know that from this definition, this weight freedom actually is stronger than log freedom, and log freedom is stronger than obstruction freedom. Okay, and so the ink example is we know it's log free and obstruction free, but it's not weight free. So here, just as a quick summary, so the two key ingredients that we have to understand which would affect termination is blocking and delay. So blocking essentially means the thread needs to wait for the environment actions, which turns Q from false to true, so that the current thread could progress. So it relies on the progress of the environment. It requires fair scheduling. For delay, it refers to the environment action that turns Q from true to false. Okay, so that the Q needs to be reestablished later. So it takes the current thread to do more loops. And so this is about non-blocking, the left branch. If we look at the blocking algorithm, and like this query example, the current thread itself cannot make Q to be true. It has to rely on the other thread to release the lock. Okay, so then the question here is, will Q ever become true? Which means, will the environment would ever turn Q from false to be true, so that the current thread to be released? And the current thread couldn't make progress. So this is essentially asking whether the blocking is temporary or permanent. And so in this simple example, this left thread, each method call of M simply acquires this lock, enters the critical region, and releases the lock. So and so T1 is blocked if T2 here is inside the critical region. So it has to wait to acquire the lock. But this blocking is temporary if the critical region always terminates, right? So so this shows this is an example of temporary blocking, and then this is a permanent blocking. So if the thread on the right side just it never release the lock, so the critical region is an infinite loop. So this is another example, probably more interesting about permanent blocking. So here we have read and write locks, and its implementation is biased against writer. So if there's always readers coming, and so for the writer, then the number of readers is always greater than 0. So it may be blocked at this point and never progress. So this may also cause permanent blocking. So here we have to discuss different cases. If Q will ever becomes true, then another question is, will Q be equals to true, eventually stable? This is exactly the same question we ask here. It worries about whether the environment will turn the Q from true to be false again. So this is essentially about the delay here, the same discussion as we have here. And if we look at this example, if this is the simple test and set based lock, so here we have this compare and swap operation, and it may always fail even if the critical region is always terminates. So the lock is always released by the environment, because it immediately after it releases the lock, it may start another round of the loop and successfully acquire this lock. Okay. So, and this is the same delay as we explained before. So it's caused by the successful case in this environment, and it may cause starvation. But if we look at a different example, we use a different implementation of lock, the so-called ticket lock. So here the first two lines implement lock acquire, and then we increment this counter, and then we release the lock. So here this ticket lock is simulating the banking system. So which means that all the clients that tries to acquire the lock actually forms a queue. So it guarantees that eventually every thread waiting for the lock will get the lock. So it's a fair implementation of lock. I'll just skip the detail here. And then, so then in different cases, so we have to, so if like for the ticket lock, it guarantees that eventually Q will be true. Each thread will get the lock. So then it guarantees the algorithm to be starvation free. So it says there's only temporary blocking and only finite delay here. And if Q could be false infinite number of times. Okay, so this is the definition of starvation freedom. It says under fair scheduling, then every object method call must return. So there's no starvation. And if we look at this part, essentially this is the same as wait freedom. So starvation freedom is just a relaxed version of wait freedom. It's essentially wait freedom. Sorry, what did I do? Yeah, it's essentially wait freedom with the assumption of fair scheduling. Okay, and if this is false, so then we like here we have to consider whether the environment is making progress. It's like this example here. So it could be may always fail, but the environment is making progress. Then in this case, we call it deadlock free. And the definition of deadlock freedom is just so under fair scheduling, there always exists some method called as returns. And if we look at this part, this is just lock freedom. So deadlock free is just lock free with assumption of fair scheduling here. And if environment is not making progress, in this case, actually there's we see there is a deadlock. Okay, and here we consider this branch. So sorry, and if Q if the blocking is permanent, Q will never become true. Then still, this is not immediately deadlock. We have to consider if the environment is making progress. If we recall this example here, so this writer is permanently blocked, but then the environment always have readers that terminates. So it's still lock-free in this case. But if the environment is not making progress, this is also deadlock. Then now we have considered different combination of blocking and delay. And so we have these 2 dimensions. And if we consider this different combination, we have all these different liveness properties. And in terms of the implication relation, we know that the weight freedom is stronger than log freedom, and log freedom is stronger than obstruction freedom. Also, it's stronger than starvation freedom, and log freedom is stronger than deadlock free, and we have this implication relation. So this is the informal characterization of these different progress properties. Now, next we have to answer the question: how do we verify them? Okay. So that's fine. Okay. So. So to verify the progress, since we already know that blocking and delay, and we propose a separate mechanism to reason about the 2 issues separately. And so first we try to reason about delay without allowing any blocking. And this allows us to prove non-blocking algorithm like log freedom or weight freedom. Then we just consider blocking without worry about delay. This allows us to prove starvation freedom. And if we reason about both, the combination of delay and blocking, we could prove deadlock freedom and some other properties here. So let's first look at what do we do with sequential verification for loops in sequential programs. So here we need to make sure there's no infinite loops. And what we do here is we could assign tokens for loops so that we ask each iteration of the loop consumes a token. It's a very trivial example. So it takes 2 rounds of the loop. Then we just assign 2 tokens. So it pays 1 token for each iteration. And since we only assign finite number of tokens, so for this example, we could never find enough tokens. So we may never prove the termination here. This is very simple. And this idea actually could be formalized using separation logic, which allows us to treat the tokens as resources. It says if P is like the loop invariant, and we're starting from the P, so P implies P prime with an extra token. So P prime has 1 less token than P. So when we reason about this loop body, we use the precondition P prime, which means whenever you enter the loop, you have to consume 1 token here. Okay. But here we don't have to worry about the formalization. We could just use this informal, show the informal idea, which requires the number of tokens decreases at each round. Okay. So, but this is for sequential program. It's too strong in the concurrent setting. And as I explained here, so this case may always fail. Whenever it fails, it requires more tokens to do more loops. But still, so we want to have this example verified because it's still a good algorithm. It's a lock-free algorithm. So how do we verify this concurrent algorithm here? We have seen this figure. So the way we reason about it is essentially there's no magic. For progress verification, we have to, we always follow the token idea to make sure that there's an infinite number of steps before we eventually see the good things happen. So here we need to worry about blocking. Then it says if we want a temporary blocking, it essentially says the thread is unblocked in finite number of steps from this environment. And if we worry about delay, it will only allow the finite number of delay here. Or in the special case, we may allow infinite number of delay or permanent blocking, but then we require the environment always make progress, which means whenever so before every time before the environment progresses, there could only be a finite number of delay and blocking here. So then to control the numbers, we just use the idea of tokens. It's just different tokens to control the blocking and delay. This is just the basic intuition. So let's first look at the way we handle delay here. As we said, this delay is acceptable for a lock-free algorithm as long as there's no infinite delay before the whole system progresses. So which means that as long as we know that the environment progresses, it's fine for the current thread to do more loops. Then the idea is still the same as before. In a sequential program, we assign loop tokens, and each round of the loop consumes one token. Then we allow the number of loop tokens to increase if we know it is delayed, okay, delayed by the environment. But then we need to prevent infinite delay before the whole system progress, okay? And to prevent infinite delay, we introduce a new kind of delay token so that whenever a thread delays others, it has to consume a delay token. And so a thread must progress before it's using up all its delay tokens. It's a second level of tokens. So this still may be a bit abstract, but this is a concrete example. Suppose here we have 3 threads. Each of them calls the ink we have seen before, the ink of the counter. Okay. Now they all want to enter this loop. So to verify this, we assign tokens to each thread. So each one has a loop token, the orange one, and then it has a delay token here. So and then so they enter the loop and consumes the delay token, and then they all tries to execute the cast. And we know in this case only one thread succeeds. Okay, and then the other 2 threads in this case will fail, so they have to do more loops. For the third thread, since its cast succeeds, so it knows it delays others. So its cast has to consume this delay token, use up this delay token. And then for the other 2 threads, since they know they are delayed, then we allow their loop token to increase. So we could reset the number of loop tokens so that they could do more loops. Essentially, you could view that you turn this delay token to more loop tokens. Okay. And actually, we could do this Hoare-style reasoning by encoding this token idea. Let me just skip the detail here. Okay. So then we could refine this loop rule. We require that the number of loop tokens must always decrease at each round of the loop. Unless it is delayed, then the number of delay tokens has to decrease. Okay. But still, this doesn't handle blocking. It handles delay. And it could reason about wait freedom and lock freedom, but it doesn't reason about blocking, because here, if we unfold this lock, if it's a spin lock, then if the lock has been acquired by others, this loop may execute infinite number. It may execute an infinite number of times, and so in this case, we cannot find a decreasing metric in advance. We cannot know how many round of loops it will execute in advance. So then to reason about blocking, actually, we first look at this part. We don't want to consider delay here. So we only consider this blocking, and then there's no no infinite number of delays, so we could verify starvation freedom. And also, it's interesting to note that probably if people know about concurrency reasoning, usually this blocking algorithm is much simpler because it's usually lock-based, and it's not non-blocking could be much more fine-grained. But if you reason about progress properties, from this figure, you could see that it's actually more complicated for blocking algorithm than the non-blocking algorithm. Okay. So here, one of the challenge to reason about the blocking algorithm is to avoid this kind of circular reasoning. Here we have an example here. We have 2 threads, and we don't need to worry about the functionality. Here, there's a while loop. It relies on the assignment of y to be 0. So it waits for y to be 0 here. And then for this while loop, it waits for x to be 0. So as we can see here, this is a standard deadlock scenario. But if we are not careful, we just follow the standard rely guarantee style reasoning, it seems we could verify it. So for this thread on the left, it says, well, I rely on the thread T2 that will set y to be 0. And then I guarantee, as T1 will guarantee that x will be 0. For T2, it relies that T1 will set x to be 0. Then it guarantees that it will set y to be 0. Then rely guarantee reasoning requires that the guarantee of one thread implies the rely condition of the other thread. Indeed, in this case, the guarantee of T2 implies rely of T1, and the guarantee of T1 implies rely of T2. It seems the rely is always satisfied. So we could have this kind of reasoning, but this is unsound for Leibniz reasoning. This is a well-known challenge. To address this problem, so here we get some insight from the starvation-free ticket lock. So in this example, whenever a client tries to acquire the lock, it waits in a queue. So there's always a finite number of threads in front of it, to acquire the lock. So then here we introduce the idea of definite actions to break this circular reasoning. The definite action is an action that will eventually happen without relying on the progress of the environment. That's why we call it definite. So it's like after the lock release, after it has been acquired. In this case, we only need to worry about the termination of the critical region. So it's not affected by the environment behavior. Then we ask each thread only waits for a finite number of definite actions. And also we require the numbers is always decreasing. Then in this case, we know that this blocking is always temporary. Okay. Yes, then we could derive the so-called starvation freedom here. And the definite action is formulated as a pair of assertions which says P leads to P prime. P is like the precondition, P prime is like the postcondition. Here in this example, it could be that P says the thread has acquired the lock. Then it guarantees that the thread will always release the lock. So, and we see it is enabled when P holds. And in this case, it's definite because when it acquires the lock, then suppose the critical region is always terminating, then P prime will always be true eventually. Okay. And then we, again here, this is a place that we have to require fair scheduling. Okay. And in this example, if we want to reason about the starvation freedom of this ticket lock, so suppose here we want to prove that T3 will eventually get the lock. It's waiting in the queue. Then, so each we have this definite action that says T1 gets the lock, then it guarantees release. It will eventually release the lock. So, and then if T1 releases the lock, it enables another definite action, which says when T2 gets the lock, T2 releases the lock. So then it enables, when T2 releases the lock, it hands, it it hands the lock to T3. So here we see it's for T3 it waits a sequence of definite actions, and this length of the definite action is always decreasing because of this fair scheduling. And then in this way we guarantee that the blocking is just temporary here. So and then if we refine this loop rule, this rule for while loop, we first need to have a specification for this set of definite actions. This is part of our specification. Then also we need to prove that this specification of definite actions is indeed correct. So the D is indeed definite. And then we say the number of loop tokens must decrease at each run unless it is blocked. Then in this case, the token doesn't have to be consumed. But then the block cannot be permanent. It means that the length of the D sequence must decrease. Okay. So what time do I have? Okay. And actually using this rule could prove more starvation freedom examples like queue locks or lock coupling lists. So it works for starvation free, but this is still too strong for deadlock free, which involves both blocking and delay. And actually in this figure, actually for deadlock free, we follow this path. Actually this means this means there might be an infinite number of delays. Also, we could follow this path. This means there could be permanent blocking here. They all allow deadlock-free algorithm. Okay. Then to handle this case, we have to reason about both delay and blocking here. And we look at our test and set log. So here, again, this delay here is caused by the successful acquire of the lock in the environment. And then here we also we want to follow if we want to follow the sequence of definite action idea, but then we cannot find a decreasing sequence of definite actions because whenever the T2 release the lock, it may immediately acquire the lock again. In this case, it's like a queue jumping. So the length of the queue is not decreasing. Then how do we handle this case? Then we basically since the environment is successful to acquire the lock, we allow this queue jump for deadlock-free algorithm, and we basically says the length of the D sequence we allow it to increase if it is delayed. So, but we need to make sure, again, there's no infinite delay before the whole system progresses. This is reusing our idea for delay tokens. So every time when a thread delays others, it has to consume a delay token. So then we have this loop rule which combines blocking and delay. It says we need to consume loop tokens for each round of a loop. But if it's blocked, it's fine to not consume it. Then the D sequence, the sequence of definite action must decrease. Or it's fine for it not to decrease. If there's a delay, then the number of delay tokens need to decrease. It's essentially a hierarchy of tokens you use to guarantee termination. Right? And then we can verify deadlock freedom following this kind of rules. So then we have a program logic which we call LADY. Actually, it combines linearizability verification and liveness. And underlying the logic is does program-aware refinement reasoning. Then the judgment is in the form of the relay guarantee style logic with extra specification of definite actions. It says the object's implementation refines some atomic object specification. This P could be viewed as object invariant. Okay, and so if we customize the specification here, like D and the number of tokens allowed in the condition P, then we could derive different property like log-free, weight-free, and dialog freedom. All these properties could be derived. Could be derived by different combination of the parameters here. Okay, so I'll also give a quick review of another extension, which is actually if we think of the previous progress properties, we always expect a method to terminate. But for the lock implementation, actually it's possible for it to never terminate, because if the environment, if other threads acquire the lock, then the acquire has to be blocked. So non-terminating is, in this case, is the expected behavior. So we call this kind of methods partial methods. And all these progress properties we explained before don't apply in this case, because they all want the method to terminate. And so we have to further extend these properties to describe the objects with partial methods. And so, for instance, one of the problems we have to address is that we have different locks. One is ticket lock, the other is one is ticket lock, the other is test and set lock. So they imply different progress properties, and we need to propose different progress to specify the locks, and the properties have to be somewhat different from here. So and then so just skip the detail. So we have a relaxed version of a progress for logs, which we call partial deadlock freedom and partial starvation freedom for this different lock implementation. So just as a quick summary, this study all the existing progress properties in the literature, and to understand them, we figure out the two key issues, which we call blocking and delay, which would affect the progress of concurrent objects. And then we also propose two new properties for these objects with partial methods, which we call partial starvation freedom and partial deadlock freedom. And we unify the verification of all these properties in our Lily framework. Okay, thank you.
Question? Yeah.
Hi, good talk. Do you have any completeness result?
No.
No, okay. And I don't know whether this makes sense, but is it possible to map verification with respect to general LTL properties to this style of logic? So you have in this work you proposed a framework for many form of lock freedom and weight freedom, starvation freedom, and many progress property. But is it possible to extend this logic, this framework, to more kind of a temporal logic property other than progress aware ones?
Yeah, sure, you could do that. Actually, so LTL is very powerful, but it's different style. This is program logic, so it's like more like syntax directed. So you could pick the right rules based on the program, the syntax of the program. But LTL, you just encode the property and the program both into the formula. So certainly you could encode all these programs and do this verification. Here, and to answer your first question, we don't intend to make it complete. Actually, this set of rules are just you could see. Yes, so this is, you could view this as just a set of common patterns, which we may use to verify these different progress properties. It's just some specialization of the common patterns. But you certainly could have more general guidelines, like there's always just encode this finite number of execution steps before it terminates. You could encode this requirement as one LTL formula, but then it could be more difficult to use it.
Okay, thank you.
More questions? Well, I have perhaps a naive question. So the problem, the question is about, step indexing is a technique that's used to deal with, can be used to deal with termination problems. So my question is, how is this related to techniques based on step indexing, later modalities, stuff like this?
Well, it's probably a different issue here. So yeah, it's the token is like a kind of index, but by step indexing, I guess you mean the so for the to handle recursive unpredictable polymorphism, this set of issues. Right. It's a different issue. It's to handle some kind of circularity at the meta level reasoning, and it's. Actually, it's still for safety. It's not very relevant to here. Thanks.
Okay.
So my question actually relates to completeness. But so no completeness is okay, but how to use that, right? So it should be that means in practice it should be useful, right?
Right.
How this kind of sequence, that means this token can be obtained. So do you have any restrictions on the programs? How can you find that, right? For example, you have example I less than 2, and inside you say have 2 tokens there.
Right.
So how do you have, or have you applied this in some practical examples? And this is quite interesting.
Yeah, this is applied to practical algorithm. But right. To answer your question, so here the specification is provided by the programmer. It's not automatically generated.
Oh, so this token, users can say, I
yeah.
define token as this. For example, I define token as I.
Yes.
I see.
Like for this.
Okay.
Okay. Yeah. I think there's an example.
Sorry,
here.
Maybe I missed something. I see. So this program does
yeah,
not.
So like in this case, we know that if there's no interference from this environment, then this loop will always succeed in one round, one iteration.
Right.
So then we only need one loop token.
Okay.
And yeah, it's like this.
Okay.
So unless there are burning final questions, then I propose we thank Xinyu again for a nice talk.